Hi everybody, this is Miss McClellan, here to go over IM2 Notes 1.3.2 with you. What is the relationship? Angles formed by transversals. Today we have two learning goals, and I'm going to write them both in the first person. Number 1. I will be able to use what I have learned about symmetry to prove the corresponding angles theorem. Period. And number 2, I will be able to, when shown a diagram of parallel lines cut by a transversal, I will be able to identify and name appropriate relationships. Period. Okay. Definitions of rigid transformations. We start with some notes to review definitions of rigid transformations. We have a word bank and a bunch of paragraphs. Okay. Functions that assign each point in the plane to a unique image point in the plane are called rigid transformations. Or motions, because they move the entire plane with any figures you have drawn so that all of the figures remain unchanged. Therefore, angle measures and segment lengths are preserved. We keep the x and y axes on an underlying plane in their original position for reference. When a polygon is transformed, the new figure is called the image. When you hear image, it means you're talking about something new. The image is often named using prime notation, for example, the image of point Q is labeled as Q with an apostrophe, and that is read as Q prime. You read the apostrophe as prime. So you read the apostrophe as prime. There are 3 basic rigid transformations that we will consider: reflections, translations, and rotations. All rigid transformations can be seen as a combination of them. First, we look at reflections. When a figure is reflected across a line, it appears that the figure is flipped over the line, like a mirror image. The mirror line is the line of reflection, shown as line L in the diagram at left. Oops. Formally, a reflection is defined as a function that assigns each point A to a unique image point A prime, so that the points in their images are equidistant from the line of reflection. In the diagram, AP is equal to A prime P. So we've done line of reflection. Next, rotations. Turning a figure about a fixed point is called a rotation. Figures can be rotated either clockwise or counterclockwise. Formally, a rotation about a point O is a function that assigns each point P in the plane a unique image point P prime. So in the drawing, we have point O, and then we have, this is point P, and after point P rotates, it arrives at its image point P prime. So that all angles of rotation, in this case, we would be doing POP prime, have the same measure. This is called the angle of rotation. And OP is equal to OP prime. Lastly, we have translations. Sliding a figure into a new position in the plane is called a translation. Formally, a translation is a function that assigns each point Q in the plane a unique image point Q prime so that all line segments connecting a point with its image have equal length and are parallel. Okay, let's get started with the notes. 1-81, Part A. Two polygons are congruent if there is a sequence of rigid transformations that carries one polygon onto the other. Describe three different sequences of rigid transformations that can be used to carry one parallelogram onto the other in Marcos's diagram. So I've outlined one of the parallelograms in pink, and I'm going to first use translation. So I'm going to translate this along an edge and drop it here, and I see that these two parallelograms are congruent because I arrived at one from another using rigid transformations. So first thing I did was translate along an edge. I started up here. Next I will, how about rotate? I'll rotate about a vertex 180 degrees clockwise. So here I have a vertex, and I don't actually have the ability to show you rotation on this, so I'm just going to draw it. I'm going to rotate 180 degrees, which would result in landing on this spot right here, and I'll call this P prime prime. And if you get to do this in class, then we'll be using tracing paper, so it'll be easier to see. Okay, for my last example, I will reflect across an edge. If I reflect across this edge, what I end up with is this shape, and that has not mapped the polygon back into its original orientation. So I actually have to reflect across an edge twice. Once horizontally and once vertically. So after I reflect here, I have to again reflect. So I'll go across this edge next, and I'll end up in my final position right here, and that's P prime prime prime. All done. Part B. Consider the angles inside a single parallelogram from the pattern. So I've blown up one of these parallelograms, and we have it pictured. Which angles are congruent? Okay, I'm just going to label all of these. 1, 2, 3, 4, 4. Okay, I know that angles 1 and 3 are congruent because I can see that they are vertical angles on my diagram. They are vertical angles in the original diagram. Same goes for angles 4 and 2. 4 and 2 are vertical, 1 and 3 are vertical. Part C. Since each parallelogram is a translation of another, what can be stated about the angles in the rest of Marcos's tiling? Color all the angles that must have equal measure of the same color. So it'll be easier for me to show you with coloring. I'll make 1 and 3 blue, and I will make 4 and 2 pink. 4 and 2. 4, 2. 4 and 2. 4, 2. 1 and 3. 1, 1 and 3. We can say that opposite angles in a parallelogram are congruent. D. What about relationships between lines? Can we identify any lines in the diagram that must be parallel? We'll mark them. Okay, parallel lines are marked with arrows. Okay, we have this direction parallel to here, little arrows all over. We use arrows to show parallel because arrows denote direction, and being parallel is all about direction. We also have parallel lines going across the page, and I'm using 2 arrows now just to say, hey, I'm talking about a different direction, so I'll use a different number of arrows. Missed a box. Done. Okay. 1-82. Julia wants to learn more about angles in Marcos's drawing and has decided to focus on just a part of the tiling. An enlarged view of that section is shown in the image below, at right, with some points and angles labeled. Can you decide which is the transversal, the one that crosses 2 or more other parallel lines? Well, if you said line JK, you would have been correct. The transversal is crossing the parallel lines. Which lines are parallel? Now, if you would have said lines LM and NP, you would have been correct. Those lines are parallel to one another, as told by the little arrows on them. Let's trace angle X on tracing paper and shade its interior. Now, let's translate angle X by sliding it along the paper until it lies on top of another angle and matches exactly. Which angle in the diagram corresponds with angle X? Angle B corresponds with angle X. In this diagram, corresponding angles, the name given to angles X and B, because they are in the same position at 2 different intersections of the transversal. What is the relationship between angles X and B? They are congruent. I know because a rigid transformation this time it was translation, maps angle X onto angle B exactly. 1-83. The corresponding angles in Julia's diagram in problems 182 are congruent because they were formed by translating a parallelogram. Ooh. See, they're formed by translating something in here, the parallelograms. Name all of the other pairs of corresponding angles in Julia's diagram. So we already have X and B, angle X and angle B, and we can find 3 more. So angle A should correspond with angle W. Angle Y should correspond with angle C. And angle Z should correspond with angle D. Notice that each time I'm talking about a new angle, I add an extra tick mark to differentiate my new angle from any angles I may have spoken about before. Part B. Suppose angle B is 60 degrees. Use what we know about angle pair relationships to determine the measure of all other angles in Julia's diagram. Okay, well, I know that the corresponding angles, which we've just identified, must all be congruent to one another. So X and B are congruent, and that's why I have that X is also 60 degrees. I also know something about vertical angles. So X is vertical to Y, and vertical angles are congruent. So X and Y should have the same measure. So since Y is vertical to X, Y and X are congruent, so angle Y is also 60 degrees. I know that angle X is 60 degrees because it corresponds to angle B. C is vertical to B, so that's also going to be 60 degrees. And what can I do to figure out the others? Well, I can see that A and C have to add to 180. These are supplementary, so 180 equals 60 plus 120. So this must be 120 degrees. A is 120. And then I think all the other ones have to be 120 because we have vertical angles and then corresponding angles helping us out. Okay, moving on. 184. Are they always congruent? So far, we've investigated transversal lines that cross pairs of parallel lines. However, transversal lines can cross any pair of lines, not just parallels. Parts A through D below. If we have enough information, we will determine the measures of angles X and Y and state their angle pair relationships. Okay. All right, well, I know that 135 degrees corresponds to angle X, and I just want to make sure that they line up perfectly. And I think they will. They do. Okay. So I have X is 135 degrees, and Y is vertical to X, so it should also be 135 degrees. We have corresponding for 135 all the way to angle X, and vertical takes angle X to angle Y. Part B. Let's see. Can I do it again? So X and 135 correspond to one another. Oh, but you know what? without parallel lines, corresponding angles don't work. So not enough information to find the measure of angle x, but we can still find the measure of angle y because this is a straight line pair. So, but 135 plus y should equal 180 because they're supplementary angles. So I'll subtract 135 from both sides. And I get that y is 45 degrees. Okay, next. This is looking good. We have parallel lines again. Let's see. Yes, parallel lines. This is reliable. I have angle x is 135. Angle x corresponds to 135-degree angle. And angle y plus 135 should again be 180 degrees because this is a straight line pair. So angle y is going to equal 45 degrees. I didn't solve this equation by hand again because it's the same as in part B. Okay, next. Let's see if I can translate that down. No, I cannot. There's not enough information again for y this time. Not enough information to find the measure of angle y because we don't have a transversal crossing parallels, and that's what we would have needed. But we can solve for x. X plus 135 degrees should again be 180. So we have x is 45 degrees because this is again supplementary and a straight line pair. Okay. Now part E. Use tracing paper to determine whether corresponding angles are congruent. Oh, we already did that. Corresponding angles are not always congruent. They're congruent when the transversal crosses parallel lines and they are not congruent when the transversal crosses lines having different slopes. (1-85). Conjectures and theorems are often written in the form if-then. A statement in if-then form is called a conditional statement. Make a conjecture about corresponding angles by completing this conditional statement. If parallel lines are crossed by a transversal, then corresponding angles are congruent. It's a conjecture because we have not formally proven it yet, but we're going to prove it right now. Part B. Complete these statements to prove the conjecture from part A is always true. There is a blank along the transversal that maps angle 1 onto angle 2. A rigid transformation. It's a translation in this case. Let's look at it. Here I am translating across the transversal, mapping angle 1 onto angle 2. Translations preserve. What is it that they preserve? Let's go back to the front. Oh yes, they preserve angle measures and segment lengths. Angle measures. So angle 1 is congruent to angle 2. Therefore, if parallel lines are cut by a transversal, then the corresponding angles are congruent. Yay! We're almost done. We're just going to go over naming polygons. Classifying polygons. We've got a word bank and we've got notes to fill in. Polygons are named according to the number of sides they have. Let's put as many of these in as we can. Okay, a 3-sided shape, triangle. Octagon, I know, is for 8 sides. Decagon, I know, is 10 sides. 11gon, it's going to be 11 sides. Nonagon, I know that means 9 sides. Looks like I'm missing one. I should have n-gon in here. An n-gon is an n-sided polygon. Okay, pentagon, I know that means 5. Pentagon. Quad, I know that means 4. Quadrilateral. Hexagon and heptagon. I know hepta is 7. Heptagon, 7-sided polygon, and hexagon must be for 6. Okay. Polygon is called blank if each pair of interior midpoints can be connected by a segment without leaving the interior of the polygon. Convex. A polygon is a regular polygon if it is convex and has congruent sides and congruent angles. Thanks for following along, everybody. That's the end of today's notes. See you next time. Bye.